The seismograph at the Pacific Northwest Seismic Network recorded the first arrival at 3:14 in the morning, and the duty scientist who was watching the monitors did what duty scientists do when a signal comes in during the quiet hours before dawn. He looked at the waveform. He looked at the amplitude. He looked at the frequency content of the signal, the way the energy was distributed across the range of wavelengths that the instrument could detect. And then he looked at the location estimate that the automated processing system had generated from the arrival times at different stations across the network, and he sat back in his chair and exhaled slowly. The location was in the tectonic region, deep in the southwestern Pacific, roughly equidistant between the coast of New Zealand and the islands of Tonga. The preliminary magnitude was 7.4. He updated the alert, notified the appropriate agencies, and began the process of refining the location and magnitude estimates that would go into the formal notification. He had been doing this work for 9 years, and he had processed hundreds of significant earthquakes. This one, on its own, was large, but not exceptional, for the Tonga-Kermadec region, which is one of the most seismically active subduction corridors on Earth. He logged it, completed the notifications, and went back to watching the monitors. 4 days later, a magnitude 6. 9 earthquakes struck off the coast of northern Japan. 3 days after that, a magnitude 7 tore through the Vanuatu Arc in the southern Pacific. And 2 days after that, as the seismological community was still processing the implications of the previous 3 events, a magnitude 7.3 ruptured beneath the Malacca Sea in eastern Indonesia. For earthquakes measuring 6, 9 or greater in 10 days, spread across 4 separate segments of the Ring of Fire, the vast horseshoe-shaped belt of subduction zones and transform faults that encircles the Pacific Ocean, and that is responsible for approximately 90% of the world's seismic energy release. Each earthquake was significant in its own right. Each one, considered alone, fell within the range of what the Ring of Fire produces regularly and would not have attracted unusual scientific attention. But 4 of them in 10 days, at different locations around the ring. Each one separated from the others by enough distance that simple aftershock mechanics could not explain the clustering. Was something that the scientists who study global seismicity patterns were not comfortable dismissing as coincidence. Not yet. Not without looking more carefully. The duty scientist in the Pacific Northwest who had processed the first event found himself, 10 days later, pulling up the global earthquake catalog and looking at the sequence laid out on a map. The 4 red circles, each one sized to represent the magnitude of its event, set at intervals around the Pacific Rim like points on a clock face. Tonga-Kermadec in the south, Japan in the northwest, Vanuatu in the southwest, Indonesia in the west. He was not the kind of scientist who reached for dramatic conclusions. He had spent 9 years learning to be careful about patterns, to test them against the statistics of random clustering before treating them as signals. But he was also not the kind of scientist who refused to ask questions when the data presented something that deserved a question. He opened a new document and began writing down what he was seeing. What followed over the next several weeks was a scientific investigation that is still unfolding, and that is producing findings that are making the people, whose job it is to understand the Ring of Fire, more watchful, more careful, and in some cases more concerned than they had been before the sequence began. The Ring of Fire is one of those features of the natural world that is so familiar, so deeply embedded in the standard curriculum of earth science education, that it is easy to understand it as a static fact rather than a dynamic system. The name conjures a clear image. A horseshoe of volcanic and seismic activity, running from the tip of South America, up the western coast of the Americas, across the Aleutian Islands, down through Japan and the western Pacific island chains, and back around through New Zealand. The image is essentially correct. The Ring of Fire is real, it is persistent, and it is where it is because of deep and enduring features of the planet's tectonic architecture. The Pacific Plate and the smaller plates that surround it are being subducted beneath the adjacent plates at their edges, diving down into the mantle where they are eventually assimilated back into the Earth's interior. This subduction is what drives the earthquakes and the volcanic eruptions that define the ring. It is what has driven them for tens of millions of years, and what will continue to drive them for tens of millions more. But the Ring of Fire is not simply a belt of independent, isolated fault systems that each operate on their own separate clocks, generating their own separate earthquakes without reference to what their neighbors are doing. The tectonic forces that drive the ring are global in scale, arising from the movement of plates that span entire ocean basins and that interact with each other across distances of thousands of kilometers. The stress fields that accumulate in one part of the ring are not completely independent of the stress fields in other parts. The Pacific Plate, which underlies much of the ring's seismic activity, is a single coherent structure whose motion is governed by forces acting on its entire surface. When that plate moves, or when the plates that bound it respond to changing stress conditions. The effects are not confined to one location. They propagate through the mechanical system, changing the loading state of structures far from the point of origin. This does not mean that every cluster of earthquakes on the Ring of Fire reflects a shared mechanical cause. The ring produces dozens of significant earthquakes every year, and statistical clustering of independent events is mathematically expected, not exceptional. If you take a system that produces earthquakes randomly at a high background rate and look at it over short time windows, you will regularly find periods that appear to have elevated activity simply because random processes are inherently lumpy and even, prone to apparent clustering, even when no underlying mechanism is producing the clustering. This is one of the most important and most frequently misunderstood aspects of earthquake science, and it is the reason that seismologists are trained to be deeply skeptical of apparent patterns before they have been tested against the null hypothesis that the pattern is a product of chance. The question that the scientists who are watching the 10-day sequence have been asking is whether this particular cluster passes that test, whether the spatial distribution of the 4 events, their temporal compression into 10 days, and the specific locations along the ring that they occurred at are consistent with what chance clustering would produce, or whether the statistics suggest something systematic is operating underneath the apparent pattern. The answer, as of the current state of the analysis, is that the statistics are not conclusive. The sequence is unusual but not statistically impossible under a chance clustering hypothesis. What is keeping the scientists watchful rather than simply filing it away as an unremarkable fluctuation is not the statistics alone. It is the statistics combined with the specific locations of the events, combined with the current loading state of the fault systems in those locations, combined with a series of findings from recent research on stress transfer mechanisms that have deepened the scientific community's understanding of how earthquakes in one part of the ring can influence the probability of earthquakes in another. The Tonga-Kermadec subduction zone, where the sequence began, is one of the most structurally extreme environments on Earth. The Pacific plate is being subducted beneath the Australian plate, along this corridor at a convergence rate that is among the fastest of any subduction zone in the world, approximately 7 to 9 centimeters per year. This rapid convergence means that stress accumulates quickly on the locked portions of the subduction interface and is released in earthquakes with a frequency and magnitude that makes the region one of the most seismically active on the planet. The historical earthquake catalog for the Tonga-Kermadec zone contains some of the largest events ever recorded, including multiple magnitude 8 and above earthquakes, and at least one event in the late 20th century that is estimated to have approached magnitude 9, the magnitude 7. For that opened the 10-day sequence was not, by the standards of this region, an exceptional event. What made it notable to the scientists who were tracking its aftershock sequence was the spatial pattern that emerged in the days following the main shock. The aftershocks did not cluster tightly around the main rupture zone in the way that a simple, single-fault rupture produces. They were distributed along a more extended corridor to the south of the main rupture, in a pattern that is more consistent with stress having been transferred along the subduction interface to adjacent segments than with simple local stress relaxation around the rupture zone. This kind of elongated, propagating aftershock distribution is a signature that seismologists have learned to pay attention to because it can indicate that the main rupture has loaded neighboring fault segments rather than simply releasing stress in a confined region. The Coulomb stress transfer mechanism is the physical process that provides the most widely accepted framework for understanding how one earthquake can influence the probability of another. When a fault ruptures, it does not simply release stress at the point of rupture and leave everything around it unchanged. The redistribution of mass that accompanies the fault slip permanently alters the stress field in the surrounding rock. In some locations near the rupture, the stress changes in the direction of failure, meaning that the rock is pushed closer to the threshold at which it will rupture. In other locations, the stress change is in the direction away from failure, meaning that rupture is made somewhat less likely. The regions of increased failure probability are called Coulomb stress shadows, and the regions of decreased failure probability are called stress shadows. The geometry of these regions depends on the orientation and slip direction of the source fault, and on the orientation of the receiver faults that might be affected by the stress change. The application of Coulomb stress transfer analyses to the Tonga-Kermadec rupture, conducted by researchers at several institutions in the days following the event, showed that the stress change from the magnitude 7.4 was positive, meaning in the direction of failure, on fault segments to the south of the rupture, along the Kermadec portion of the subduction zone. This finding was noted and discussed in the scientific community. It was not alarming on its own. Coulomb stress changes from moderate to large earthquakes are routinely positive on some neighboring structures, and the fact that the stress change is positive does not mean that rupture of the neighboring structure is imminent or inevitable. The stress change is typically small, relative to the total stress that has accumulated on a fault over decades or centuries of loading. What Coulomb stress transfer analysis provides is not a prediction but a modification of the probability distribution. It shifts the likelihood of future ruptures slightly higher on the structures that received positive stress changes and slightly lower on the structures that received negative stress changes. What gave the Tonga-Kermadec analysis additional significance in the context of the 10-day sequence was that the subsequent events appeared in their locations to be at least partially consistent with the stress changes predicted by the analysis. The Vanuatu earthquake, which occurred 7 days after the Tonga-Kermadec event, is in a region of the subduction system that receives positive Coulomb stress changes from major Tonga-Kermadec ruptures given the geometry of the two fault systems. This does not mean that Tonga-Kermadec earthquake caused the Vanuatu earthquake. The causal language is too strong for what the physics can establish. What it means is that the Tonga-Kermadec rupture produced stress changes in the direction that would advance the timing of a rupture that was going to happen eventually anyway, and that a Vanuatu earthquake occurring within days of a major Tonga-Kermadec event is geometrically consistent with that stress transfer having played a role in the timing. Whether it did play a role, or whether the proximity in time is coincidental, is a question that cannot be definitively answered from the data. It is, however, a question that is worth asking carefully. The Japan earthquake, which struck 4 days after the Tonga-Kermadec event, is the most geographically distant of the 4 events, and the one that presents the greatest challenge to any mechanistic explanation based on simple Coulomb stress transfer. The distance from the Tonga-Kermadec region to the offshore northern Japan location, where the magnitude 6.9 occurred, is approximately 8,000 kilometers. At that distance, the static stress change from the Tonga-Kermadec earthquake is vanishingly small, far too small to advance the loading state of a fault segment by any measurable amount. If the Japan earthquake is part of a mechanically connected sequence rather than a coincidental temporal cluster, the connection cannot be through the static stress transfer mechanism. This brings into consideration a different class of mechanism, one that has received increasing scientific attention in recent years, and that is both more speculative and more potentially significant than Coulomb stress transfer. The mechanism is dynamic stress triggering, which operates through the passage of seismic waves rather than through the permanent redistribution of static stress. When a large earthquake occurs anywhere on Earth, the seismic waves it generates travel through the planet, crossing ocean basins and continental interiors, diminishing in amplitude as they travel, but remaining detectable at great distances. For the largest earthquakes, these waves can travel multiple times around the Earth before dissipating to below the detection threshold of sensitive seismicity. As these waves pass through a region, they temporarily alter the stress state of the rock they are moving through, compressing and extending the crust in alternating cycles as the waves oscillate past. In most cases, these transient stress changes are too small and too brief to trigger earthquakes in the regions they pass through. But in regions where faults are already critically stressed, where the accumulated tectonic loading has pushed the fault close to its failure threshold, even a small, transient stress change can provide the final increment needed to initiate rupture. The evidence for dynamic triggering of earthquakes at large distances from major earthquakes is now well established in the scientific literature, though the mechanism remains an active area of research. Following the 2002 Magnitude 7.9 Denali earthquake in Alaska, seismicity rates increased in Yellowstone and other geothermal regions across the western United States as the surface waves from the Denali event passed through. Following the 2004 Magnitude 9.1 Sumatra earthquake, triggered seismicity was observed in numerous locations around the world in the hours and days after the event, at distances of thousands of kilometers from the source. The common thread in these observations is that dynamic triggering appears to preferentially affect regions where fluids play a significant role in the crustal-mechanics, volcanic and geothermal areas, regions with high pore fluid pressure in fault zones, areas where the fault is already near the critical stress threshold. These are precisely the conditions that characterize many of the seismically active regions along the Ring of Fire. The seismic waves from the Tonga-Kermadec magnitude 7.4 would have reached the northern Japan region within approximately 15 to 20 minutes of the source event, well within the time frame that dynamic triggering operates on. The timing of the Japan earthquake, 4 days after the Tonga-Kermadec event, is too long for direct dynamic triggering from the initial wave passage to provide a complete explanation. But the relationship between dynamic triggering and subsequent earthquake activity is not always immediate. Research on the mechanisms by which transient stress changes can influence longer-term earthquake probability suggests that the passage of seismic waves can mobilize crustal fluids, alter the pore pressure distribution in fault zones, and produce slow slip-on critically stressed fault segments that subsequently evolves into a larger rupture over a period of hours, 2 days. These are mechanisms that do not require the earthquake to occur during the wave passage itself, but that allow the wave passage to set in motion a chain of processes whose final expression is a delayed earthquake. This is speculative terrain, and it is important to be clear about the degree to which it is speculative. The mechanisms described above are physically plausible and have observational support from specific well-documented cases, but they have not been established as reliable predictive tools. The scientific community does not have a quantitative model that can take the seismic wave field from a source earthquake and predict with confidence which distant fault segments will be triggered and when. What the research provides is a framework for understanding how connections between distant fault systems might operate, and a set of case studies that demonstrate that such connections are real. The 10-day sequence on the Ring of Fire is being examined in the light of this framework. It is a data point that will contribute to the refinement of the framework. It is not, on its own, proof that the framework applies to this specific sequence. The Indonesia earthquake, the fourth in the sequence, struck in the Molucca Sea region, which is one of the most structurally complex seismic environments in the world. The Molucca Sea sits at the junction of multiple tectonic plates, including the Philippine Sea Plate, the Pacific Plate, the Australian Plate, and a collection of smaller microplates and terrains whose boundaries and relative motions are still being mapped and refined by In this environment, multiple fault systems of different orientations and different slip styles intersect and interact in ways that are not fully resolved by any current tectonic model. Earthquakes in the Molucca Sea region have historically been associated with complex ruptures that involve multiple fault strands operating simultaneously or in rapid succession, precisely the kind of behavior that makes post-hoc analysis of their causes and consequences difficult. The magnitude 7.3 that struck in this region on the 10th day of the sequence added another dimension to the pattern that the scientists were tracking. The Molucca Sea is not in a simple geometrical relationship to the three preceding events in the way that might be expected if the sequence reflected a simple propagating rupture front along a single subduction zone. It is in a different tectonic environment, operating under a different stress regime, responding to a different balance of driving forces. Its inclusion in the sequence, if the sequence is indeed mechanically connected rather than coincidental, requires an explanation that accommodates the structural diversity of the four events, rather than one that forces them all into a single, simple model. This structural diversity is one of the reasons that the scientists watching the sequence are being careful not to overinterpret what they are seeing. The temptation to construct a unified narrative to say that event A caused event B, which caused event C, which caused event D, is strong because narrative is how human beings understand complex systems. But the physical reality of how stress interacts across the Ring of Fire is more complex than any linear causal chain can fully represent. The ring is a system of multiple interacting subsystems, each with its own history, its own current loading state, and its own sensitivity to perturbations from neighboring structures. When multiple elements of this system show activity in a compressed time window, the appropriate scientific response is not to immediately identify a mechanism that connects them all, but to ask whether such a mechanism is consistent with the available evidence, and to hold that question open while accumulating more data. The data that the scientists are accumulating includes not only the catalog of the four main events and their aftershocks, but also a broader picture of the seismic environment across the Ring of Fire during the period surrounding the sequence. Background seismicity rates, the cumulative count of smaller earthquakes that are too modest to attract attention individually but that collectively describe the loading state of the fault system, were elevated in several regions along the ring in the weeks before and after the 10-day sequence. GPS measurements from the network of continuously recording ground deformation stations that now covers much of the Ring of Fire showed subtle but detectable changes in the rate of surface deformation in some areas. During this period, satellite-based interferometry synthetic aperture radar data, which measures millimeter-scale changes in the shape of the Earth's surface over time, was being processed to look for evidence of slow slip events or other forms of a seismic deformation that might be accompanying the seismic activity, without being directly captured in the earthquake catalog. This multi-instrument, multi-method approach to understanding the current state of the Ring of Fire reflects the significant advances in observational capability that the geophysical sciences have made over the past 2 decades. The tools available to today's earthquake scientists would have been unimaginable to the researchers who first mapped the Ring of Fire in the mid-20th century. Dense seismic networks, with continuous digital recording and automated detection algorithms, can identify and locate earthquakes that would have been invisible to earlier generations of instruments. GPS networks with centimeter or better positional accuracy can detect the slow, steady accumulation of strain on locked fault segments, and the occasional transient acceleration that signals changing stress conditions. Satellite radar, interferometry, can emit surface deformation across entire fault systems between satellite passages separated by days or weeks, providing a regional perspective on how the ground is moving in response to tectonic forcing. The combination of these tools has produced a scientific picture of the Ring of Fire that is richer, more detailed, and in many ways more complex than anything that was available when the basic framework for understanding the ring was established. The Cascadia subduction zone sits at the northern end of the Ring of Fire, running from northern California through Oregon and Washington and continuing into British Columbia. It is where the Juan de Fuca plate dives beneath the North American plate, and it is the source of the largest earthquakes that have affected the Pacific Northwest in the geological past. The most recent full rupture of the Cascadia subduction zone occurred on January 26, 1700, producing an earthquake that is estimated to have reached magnitude 9 and generating a tsunami that crossed the Pacific Ocean and arrived on the coast of Japan approximately 10 hours later. Japanese historical records that document the arrival of this tsunami without any preceding local earthquake have allowed researchers to pinpoint the date of the Cascadia earthquake with extraordinary precision for events that predates seismological instrumentation by more than 2 centuries. The Cascadia subduction zone is not directly implicated in the 4-earthquake sequence that is the subject of this investigation. The sequence occurred entirely in the western and southwestern Pacific, thousands of kilometers from the Cascadia region. But the scientific attention being given to the sequence is in part driven by the broader question of how seismically active periods on the Ring of Fire relate to the loading state of specific segments like Cascadia that have not produced a major event in more than 3 centuries. The Cascadia fault has been accumulating stress since 1700. The GPS measurements that track the slow deformation of the Pacific Northwest landscape show the signature of a locked subduction zone, the coastline moving slightly landward as the locked fault accumulates elastic strain. The pattern of surface deformation that is expected to reverse dramatically when the fault finally ruptures and the accumulated strain is released. The specific question that the current Ring of Fire activity is prompting some researchers to examine is whether the global pattern of seismicity provides any information about the relative proximity of major subduction zones to their failure thresholds. The idea that periods of elevated global seismicity might be correlated with subsequent large earthquakes in specific regions is not new, and it has not been established as a reliable forecasting tool. The statistical analysis required to test such a correlation properly is complicated by the fact that the catalog of major subduction zone earthquakes is short relative to the recurrence intervals of the events, meaning that the sample sizes available for analysis are small. What the current period of activity is providing is a data point that will eventually be incorporated into this statistical picture, regardless of whether a major Cascadia earthquake follows in the near term or in the more distant future. The probability estimates that are used in official seismic hazard assessments for the Cascadia subduction zone are derived from the paleoseismic record, the geological evidence of past earthquakes preserved in coastal sediments, offshore turbidite deposits, and the stratigraphy of coastal marshes and lakes. These probability estimates are long-term averages that express the likelihood of a major rupture occurring within a given time window, typically expressed as a percentage probability over the next 50 years. The current estimates place the probability of a major Cascadia earthquake, defined as an event with a magnitude of 8 or greater, at somewhere between 10 and 15% over the next 50 years, with higher probabilities for partial ruptures of specific segments of the zone. These numbers are not changed by the occurrence of the 4-earthquake sequence in the Western Pacific. They are derived from the Cascadia system's own loading history and from models of how that loading relates to earthquake probability. What the 4-earthquake sequence does is remind researchers and emergency managers that the Ring of Fire is an active system, and that the quiet that characterizes the intervals between major earthquakes in any one location is not a permanent condition. The Pacific Northwest is not the only region along the Ring of Fire where the 10-day sequence has prompted closer examination of current hazard conditions. The Japan earthquake in the sequence occurred in a region that has been under intense scientific scrutiny since the March Tohoku earthquake, a magnitude 9 event that remains the most powerful earthquake in Japan's recorded history. The event that triggered the tsunami that devastated the northeastern coast of Honshu and that caused the Fukushima Daiichi nuclear power plant disaster. The Tohoku earthquake and its aftermath produced a transformation in Japanese seismology and earthquake engineering, comprehensive reassessment of the hazard posed by the Japan Trench subduction zone that continues to generate new findings. The magnitude 6.9 that occurred in the 10-day sequence struck in the offshore northern Japan region that is part of the same broader subduction system that produced the 2011 event. And while a 6.9 is a significantly smaller earthquake than the magnitude 9 Tohoku earthquake, its occurrence in this region carries a weight of context that makes it something more than just another entry in the catalog. The research on the Tohoku earthquake has established in extraordinary detail how the stress field along the Japan Trench evolved in the years before 2011 and how it has evolved since. The fault segments that were locked before Tohoku and that ruptured during the event have been mapped with high precision. The segments that did not rupture in 2011 but that received stress changes from the event have been identified and their current loading states assessed. The GPS network in Japan, which is the densest continuous GPS network in the world, has been measuring the post-Tohoku deformation of the Japanese archipelago with millimeter precision, providing a detailed picture of how the crust is responding to the stress redistribution caused by the 2011 rupture and how the loading is evolving on fault segments that have not yet ruptured. The magnitude 6, 9 in the 10-day sequence occurred in a region where this post-Tohoku loading analysis had identified elevated stress, where the GPS measurements had documented deformation patterns consistent with stress accumulation, and where the background seismicity had been elevated relative to pre-Tohoku levels. Its occurrence is therefore not entirely surprising from the perspective of the post-Tohoku stress redistribution picture. It is consistent with the ongoing adjustment of the Japan Trench fault system following the 2011 rupture. Whether its occurrence in the same 10-day window as the other 3 earthquakes reflects a connection to those events, or simply coincidental timing within its own long-term loading cycle, is a question that the Japan seismological community is examining carefully. The scientific community's response to the 10-day sequence has been characterized by a quality that is both its greatest strength and its most frequent source of misunderstanding in public communication about earthquake hazard. That quality is disciplined uncertainty. The researchers who are analyzing the sequence are making careful, conditional, probabilistic statements about what they observe and what mechanisms might explain it. They are explicitly distinguishing between what the data shows, what the data is consistent with, and what the data proves. They are acknowledging the limitations of their methods and the incompleteness of their current understanding. They are being, in short, scientific in a precise and careful sense that is designed to produce reliable knowledge over time, but that can be frustratingly unsatisfying. For audiences who want clear answers about whether something bad is going to happen, this quality of disciplined uncertainty is what makes the scientists watching the sequence careful rather than alarmed, watchful rather than panicked. They are not saying that the 4th quake sequence is a harbinger of imminent catastrophe. They are saying that it is a pattern that deserves careful analysis, that the mechanisms that might connect the events are physically plausible and observationally supported in other contexts, and that the Ring of Fire is currently in a period of elevated activity that is worth monitoring closely. These are honest and calibrated statements about the current state of scientific knowledge. They are not the dramatic proclamations that public interest in earthquake science sometimes creates pressure for scientists to make, and they are not the dismissive reassurances that institutional caution sometimes creates pressure for scientists to issue instead. The tension between what the science can honestly say and what audiences want to hear is one of the persistent challenges in communicating earthquake hazard. Earthquakes are among the most feared natural hazards precisely because they are unpredictable in the short term. The tectonic forces that drive them are implacable and continuous. The faults that release them are invisible and silent in the intervals between events. The gap between knowing that a fault exists and knowing when it will next rupture can span centuries of human experience during which the hazard is real and acknowledged but operationally distant enough that it becomes difficult to maintain the preparedness posture that the hazard demands. When something happens, when a cluster of major earthquakes appears on the global seismicity map in a compressed time window, the human response is to want to know what it means, whether it is a warning, whether something larger is coming, whether the cluster is random or systematic. The scientists watching the sequence cannot answer these questions with the certainty that would be most useful. What they can do is describe the physical mechanisms that might be operating, assess the current loading state of the fault systems involved, and communicate the range of possible interpretations with appropriate acknowledgement of the uncertainties. This is what they are doing, and it is, in the context of the full complexity of what they are trying to understand, a significant achievement, even if it falls short of the definitive answers that the situation seems to demand. The Ring of Fire has been producing earthquakes for millions of years. The geological record preserves evidence of individual events going back hundreds of millions of years. In the deformed rock that records the accumulated strain of ancient subduction zones, in the metamorphic minerals that form only under the pressure and temperature conditions found in subducting slabs, in the volcanic deposits that mark the locations where subducted material was eventually melted and erupted at the surface. The Ring of Fire is not a temporary or transitional feature of the planet's geology. It is a fundamental expression of how the Earth works, how the tectonic plates that make up the surface of the planet are continuously created and pushed outward by the addition of new material, and eventually subducted back into the mantle at the ring's convergent margins. This process has been operating since the earliest stage at which the Earth had a differentiated mantle and crust capable of producing distinct plates. and it will continue operating long after the current configuration of continents and oceans has been replaced by whatever comes next in the planet's slow tectonic evolution. Within this vast temporal context, the 10-day sequence of 4 major earthquakes is a moment, a brief acceleration, in a process that is continuous and relentless. The Ring of Fire does not become more dangerous because of the sequence. It was already dangerous. It will remain dangerous after the sequence has been analyzed and understood and incorporated into the scientific record. What the sequence does is remind us, with the particular vividness that comes from specific dated events in specific named locations, that the danger is current and ongoing, that the forces that produce major earthquakes are active right now, not in some abstract geological future, but in the present moment. This reminder has value that is independent of whether the sequence turns out to reflect mechanical connections between the events or simple statistical clustering. If the connections are mechanical, the scientific understanding of how the Ring of Fire operates as a system will be advanced in ways that improve future hazard assessment and, eventually, preparedness. If the connections are coincidental, the reminder that the ring is active and capable is still accurate and still useful. In either case, the populations that live along the Ring of Fire are better served by the scientific community examining the sequence carefully than by dismissing it as the specific populations that live along the segments of the Ring of Fire affected by the 4 earthquakes in the sequence are not abstract. The Tongakar-Madak region, where the sequence began, encompasses island communities in some of the most geographically isolated and economically vulnerable parts of the Pacific. Japan's northeastern coast, which the second earthquake in the sequence affected, is still in the long process of recovering from the 2011 Toku disaster, a recovery that has been measured in the rebuilding of physical infrastructure and in the slower and less quantifiable rebuilding of communities that were shattered by the combination of the earthquake, the tsunami, and the nuclear disaster that followed. Vanuatu, where the third earthquake struck, is an archipelago nation of extraordinary natural beauty and limited resources, where the capacity to respond to and recover from major seismic events has historically been constrained by the absence of the institutional infrastructure and financial resources that wealthier nations bring to disaster response. And Indonesia, site of the fourth earthquake, is a nation of extraordinary geological and cultural diversity, stretching across a vast archipelago that sits at one of the most tectonically complex junctions on the Ring of Fire, with a history of catastrophic earthquake and tsunami events that includes the Sumatra earthquake and the Indian Ocean tsunami that killed approximately 230,000 people in 14 countries. For the people who live in these places, the 10-day sequence was not an abstract scientific event. It was a series of moments of fear, of checking for damage, of reaching out to family members in other parts of the island chain, of watching the sea for any sign of change, of waiting for the shaking to stop, and then assessing what had changed and what remained the same. The scientists watching the sequence closely are watching it on behalf of these people, in the sense that the understanding they are working to develop is ultimately aimed at improving the warning systems and the hazard assessments and the preparedness infrastructure that determine how well communities along the Ring of Fire can survive the next major event. The specific concern that the scientists are carrying as they continue to monitor the Ring of Fire in the weeks following the 10-day sequence is not that a single catastrophic earthquake is imminent. The probability of any specific major earthquake occurring on any specific day is always low, regardless of the background seismicity pattern, because the timescales of fault loading are so long relative to human experience that the daily probability of rupture is necessarily very small, even for faults that are approaching their failure threshold. What the scientists are carrying is a more diffuse and harder to communicate concern, a sense that the Ring of Fire is in a period of elevated activity that warrants sustained careful attention, that the connections between the 4 events in the sequence may be providing early information about the loading state of the ring's fault systems, and that these systems most likely to produce the next major event include segments that are home to millions of people whose preparedness for that event is, in many cases, incomplete. The GPS measurements are being watched. The seismicity catalogs are being updated in real time. The satellite deformation data is being processed. The stress modeling is being refined as better fault parameters become available. The community of scientists who study the Ring of Fire is doing what that community does in the quiet between earthquakes and in the active periods when the ring reminds them why their work matters. They are looking carefully at everything the data can tell them about the current state of the system. They are being honest about what they do not know. And they are working toward the understanding that, applied through building codes and early warning systems and public education and infrastructure investment and emergency preparedness planning, translates the knowledge of earthquake science into the protection of human lives. The duty scientist who processed the first earthquake in the sequence at 3:14 in the morning has spent the week since that night looking at the full picture of what followed. He has read the preliminary analysis of the Coulomb stress changes. He has reviewed the arguments for and against dynamic triggering as a mechanism for the Japan event. He has examined the stress transfer models that might connect the Tonga Kermadec event to the Vanuatu sequence. He has noted the structural complexity of the Molucca Sea earthquake and the challenges it presents to any simple, unified explanation of the sequence. He has been, throughout this period, neither alarmed nor dismissive. He has been watchful, which is what the data warrants and what his training and his 9 years of experience have taught him to be. The Ring of Fire is not done. It has never been done, and it will not be done in any time frame that is meaningful for the people who live along it. For major earthquakes in 10 days is a pattern that deserves the careful attention that the scientific community is giving it. Whether it reflects mechanical connections between distant fault segments, random clustering in a high activity seismic system, or some combination of the two, will be answered gradually as the analysis matures and as the Ring of Fire continues to express itself in the data streams that the global seismic network is collecting every second of every day. The scientists are watching closely. The data will speak in its own time. And the communities along the ring will do what they have always done. What communities built on tectonically active ground have always done throughout human history. They will carry on living their lives in the most beautiful and dangerous geological environment on Earth. And they will prepare as well as the science and the investment and the political will available to them allow. For the next time, the ground moves. The first earthquake in the sequence has settled into the catalogue. Its aftershock sequence is decaying in the expected manner. Smaller and smaller events, becoming less and less frequent, as the crust around the rupture zone gradually adjusts to its new stress state. The duty scientist's log from the night it arrived records the arrival time, the location, the preliminary magnitude, and the notifications he sent. It does not record the moment when he looked at the 4 circles on the global map 10 days later and began asking questions. But the questions are being asked, and the answers, partial and uncertain as they currently are being assembled into a picture of a system that has been operating since before our species existed, and that will continue operating long after we are gone. The Ring of Fire produced 4 major earthquakes in 10 days. Scientists are watching closely, as they should be. The seismograph at the Pacific Northwest Seismic Network recorded the first arrival at 3:14 in the morning, and the duty scientist who was watching the monitors did what duty scientists do when a signal comes in during the quiet hours before dawn. He looked at the waveform. He looked at the amplitude. He looked at the frequency content of the signal, the way the energy was distributed across the range of wavelengths that the instrument could detect. And then he looked at the location estimate that the automated processing system had generated from the arrival times at different stations across the network, and he sat back in his chair and exhaled slowly. The location was in the Tonga Kermadec region, deep in the southwestern Pacific, roughly equidistant between the coast of New Zealand and the islands of Tonga. The preliminary magnitude was 7.4. He updated the alert, notified the appropriate agencies, and began the process of refining the location and magnitude estimates that would go into the formal notification. He had been doing this work for 9 years, and he had processed hundreds of significant earthquakes. This one, on its own, was large, but not exceptional, for the Tonga Kermadec region, which is one of the most seismically active subduction corridors on Earth. He logged it, completed the notifications, and went back to watching the monitors. 4 days later, a magnitude 6. 9 earthquakes struck off the coast of northern Japan. 3 days after that, a magnitude 7 tore through the Vanuatu arc in the southern Pacific. And 2 days after that, as the seismological community was still processing the implications of the previous 3 events, a magnitude 7.3 ruptured beneath the Molucca Sea in eastern Indonesia. For earthquakes measuring 6, 9 or greater in 10 days, spread across 4 separate segments of the Ring of Fire, the vast horseshoe-shaped belt of subduction zones and transform faults that encircles the Pacific Ocean, and that is responsible for approximately 90% of the world's seismic energy release. Each earthquake was significant in its own right. Each one, considered alone, fell within the range of what the Ring of Fire produces regularly and would not have attracted unusual scientific attention. But 4 of them in 10 days, at different locations around the ring. Each one separated from the others by enough distance that simple aftershock mechanics could not explain the clustering. Was something that the scientists who study global seismicity patterns were not comfortable dismissing as coincidence. Not yet. Not without looking more carefully. The duty scientist in the Pacific Northwest, who had processed the first event, found himself, 10 days later, pulling up the global earthquake catalog and looking at the sequence laid out on a map. The 4 red circles, each one sized to represent the magnitude of its event, set at intervals around the Pacific Rim like points on a clock face. Tonga Kermadec in the south, Japan in the northwest, Vanuatu in the southwest. Indonesia, in the West. He was not the kind of scientist who reached for dramatic conclusions. He had spent 9 years learning to be careful about patterns, to test them against the statistics of random clustering before treating them as signals. But he was also not the kind of scientist who refused to ask questions when the data presented something that deserved a question. He opened a new document and began writing down what he was seeing. What followed over the next several weeks was a scientific investigation that is still unfolding, and that is producing findings that are making the people, whose job it is to understand the ring of fire, more watchful, more careful, and in some cases more concerned than they had been before the sequence began.